Hello, welcome back. Some of the topics we want to get into this note and some other ones are what is energy, how do you get it, and where does it go? So here we've got a guy who's pulling a bus and pulling on a bus, and this person is doing work, assuming that the bus is doing what? Well, he's exerting a large force, it looks like, by the way his muscles are bulging. But he's only doing work if the bus is moving, because there's got to be force and distance. If the distance is 0, meaning it's not moving, then the work done is 0. So, and where does he get his ability to do this work? Where does it to pull on the bus and make it move? Energy is the answer. And where does he get his energy from? Well, from the food he eats and that sort of thing. So that's sort of the topic today is energy. If I were to take a sledgehammer like so and lift it up, it has the ability to do work on something else, meaning it can push on the can and make it move. It can exert a force on the can and crush it and condense it. And there it is doing work on the can. We say when it's lifted, it has energy, which is the ability to do work. And that state that it has when it's up is what we call energy. So energy is the ability to do work. It is a state or a condition of an object in such a way that it can push on an object and make it move. And if it fits that requirement, we say it has energy. There's lots of different forms of energy. We're only going to cover some of them in this class. There's this cheeseburger, which gives us energy, which is chemical potential energy. There's this bow which has been drawn back, and that's elastic potential energy. There's the energy running through these wires, which we would be considered electrical energy. There's this water which has been dammed up, which is very, very high, the water is, and that's gravitational potential energy. There's the energy of this moving car, which is kinetic energy. And the energy of the squish spring, which would be another example of elastic potential energy. So mechanical energy, which is what we're going to be focused on, and the other type of energy that we're not really going to be getting into very much is heat. We'll talk about it and say some energy gets converted to heat, but we're really going to be focusing on mechanical energy, which has two types. Potential energy, which is energy due to the position or configuration of an object, and the kinetic energy, which is the energy due to the motion or velocity of an object. And we're going to start out with potential energy. And one thing I want you to keep in the back of your mind is that work equals the change in energy. If you do 100 joules of work on something, then you've changed its energy by 100 joules. So we mentioned that kind of early on. I just want to kind of keep mentioning that because that is kind of an important topic. So that is the deal. So here we've got a bow, and we've drawn it back, and in doing so, this thing has potential energy due to the potential or configuration, the way that it's shaped. It has energy and it can do work on something else. What would the bow do work on? It would do work on the arrow. It could exert a force on the arrow and make it move. So therefore, it would be doing work on the arrow. And how does this bow get this energy to do work on the arrow? Well, that's when it's drawn back. And what do we do when it's in order to draw it back? What do we have to do? We have to do work. We have to exert a force on the string, and we have to make the string move. So in doing that and drawing it back, we do work on the bow, and we store energy. So if we do 10 joules of work drawing the bow back, we're going to store 10 joules of elastic potential energy in the bow. Okay. Something to keep in mind is because position or configuration is always compared to another situation. I'm here versus there. Potential energy is always compared between another state. For example, when we say that this bow has 10 joules of energy drawn back, what we mean is it's got 10 joules of potential energy compared to its undrawn state. Now, does it still have some potential energy in this state? It probably does. I mean, the string is still taut, and the string isn't loose in this, so it has some energy compared to like the cut string state. But what we're going to say is it's got 10 joules of energy more in the drawn state compared to the undrawn state. So let's say we do 10 joules of, or we've stored 10 joules of energy in drawing the string back 0.5 meters. With what force was the string drawn? Well, since the bow has been given 10 joules of potential energy, that means we did 10 joules of work. And we know that work is equal to force times distance. Okay, so we know we did 10 joules of work. Okay, we're looking for what force the string was drawn back with, and we know it was drawn back a half of a meter. Okay, so when we divide by both sides by 0.5, we're going to get that the force is equal to 20 what? What do we measure force in? Newtons, 20 newtons. So just kind of the basic problem with elastic potential energy. The key thing that we want to keep in mind is that work equals a change in energy, and work is equal to force times distance. The energy stored in changing the shape of an object that go back to the original shape once that force is removed is said to be, their objects are said to be elastic. They have a natural shape, and if you change their shape, they want to go back to that shape. So, and the energy stored in deforming those is called elastic potential energy. And every object is elastic to some degree. Even things like stone and concrete will deform and bend a little bit. Some objects are really elastic, like the elastic bands. But even things like concrete will bend and want to go back to its original shape when that force is removed. So whenever we do work, we change the energy in an object. So does it take work to lift an object up? Is there a force? Yeah, you got to overcome its weight. Force of mass times gravity. And does it move? Yeah, if you lift it, it does. So when we do work by lifting an object up against gravity, the type of energy that's stored is known as gravitational potential energy, henceforth referred to as GPE, because it's easier to write GPE than gravitational potential energy. So here's the shuttle, which is gaining gravitational potential energy, and that rocket exhaust, all that energy is being expended to give the shuttle that GPE. So let's say we want to figure out how much work is done to lift a 30-kilogram rock up 2 meters. Okay, well, we want to figure out work, so work is equal to force times distance. Am I given the force? No, but I'm given the mass, and anytime you're given the mass, you can calculate the weight, which is a force. So the force of gravity is equal to mass times gravity, as always. So that's the 30 kilograms times 9.8, which is 294 newtons. And then we calculate the work done by taking that force, the 294 newtons, multiplied by 2, and we get 588 joules. Okay, so I did 588 joules to lift that object up. Okay, and the question is, how much potential energy does it gain? How much GPE does it gain? Well, remember, work is equal to the change in energy. Okay, it's equal to force times distance, but it's also equal to the change in energy. So if I did 588 joules of work to lift that up, that means I changed its energy by 588 joules. Okay, so that's how much GPE it gained. And notice what I did here to figure out how much GPE it gained. I took the mass times gravity and I multiplied by the distance that it was elevated. I took mass times gravity, which was the force, and I multiplied by the height that it achieved. And that's the equation for GPE. It's really just the equation for how much work is done to lift it up. Force times height, force times distance. So it's mass times gravity times height. And that's an equation that you're going to want to know. You're going to want to have handy. So GPE equals mgh. Okay. And really that's just the equation for the work done to lift it up. Okay. Energy, when you calculate an answer for energy, it's also going to have the same units as work. It's going to be measured in joules or Newton meters. Usually we refer to it as joules. And that So let's say we had a problem. We had a 5 kilogram rock lifted up 2 meters. How much PE does it gain? Okay, well, the equation that we just learned is GPE equals mgh, mass times gravity times height. Okay, mass times gravity times height. So that's going to equal 98 joules. Okay? And then remember, energy is measured in joules. So now that's how much energy it has, quote unquote. Okay? Now, when we say that's how much energy it has, what we really mean is it's got 98 joules of energy more than it does down here on the ground. Okay? But if I showed you that there was actually a lower elevation, does that suddenly give this thing more energy? Does it suddenly start glowing with more energy because you can see this now? No. Okay, it would have more energy, GPE, relative to this lower state. Okay, but compared to this state, it still has that 98 joules. So here's a question like you might see on a multiple choice. In which position does the rock have the most GPE, the most potential energy, given that all elevations are 3 meters above the ground? Okay, so here I lift it straight up and just heave it up. Here I lift it, push it up this incline, and here I move it up a set of 3 steps. And the question is, which one has the most GPE? Well, what we just learned is the GPE is equal to mass times gravity times height. Okay, so this is the same rock, so it's got the same mass. We're on the same planet, so we've got the same gravity. And we've got the same height, which is 3 meters. Okay, so the rock is going to have the same amount of GPE in all 3 situations. It's all the same. Okay, and if there's no friction, it would take the same amount of work to lift the rock up to each one, because work equals the change in energy. Even up this long ramp, I would use less force, but I would have a greater distance. And when we start talking about simple machines are just a trade-off between force and distance. Okay, so 2 magnets repel each other, and so they're pushing away from each other. What would you do to increase their potential energy? Which way would you move them? Towards each other or away from each other? Okay, you would move them towards each other because you'd be working against that magnetic force, and they would have magnetic potential energy. Now, if you flip one around, okay, now you would increase the energy by pulling them apart. Okay, and you would increase their magnetic potential energy that way. Okay, so what I'd like you to do is do worksheet 6-2. As always, show work for your math, and good luck.